Hello everyone. This is the first lesson of the second term. We're going to discuss about projectile motion, vertical projectile motion. A vertical projectile motion in one dimension. What is a projectile? A projectile is an object in which the only force acting is gravity. It deals with objects that fall straight down, straight up, and fall. So, which means the object is moving up and down. That's why it is called one dimension, up and down, along one line. An object is moving in free fall. So what is a free fall? Free fall is a motion in which the only force acting on an object is gravity. Gravity is the force, of course, that the earth exerts on an object that is above its surface. So gravity is always acting downwards, whether the object is moving up or down. The acceleration of this object due to gravity is called gravitational acceleration, and it is equal to 9.8 meters per second squared here on planet Earth. The object slows down as it moves up against gravity. The object speeds up as it moves downwards in the direction of gravity. So now we apply the equations of motions to calculate the quantities that are involved in the motion. So A is replaced by G, which is gravitational acceleration. Delta X of the equations of motions is replaced by delta Y. V final is equal to V initial plus GT. V final squared is equal to V initial squared plus 2G delta Y. Then the third equation is delta Y equal to V initial delta T plus half G delta T squared. The last equation is delta Y equal to V initial plus V final all over 2 times delta T, where Vf stands for the final velocity, which is measured in meters per second. Vi is the initial velocity, which is measured in meters per second. G is the gravitational acceleration. Its value is 9.8, and it is measured in meters per second squared. Delta T is the time taken between 2 points, which is measured in seconds. Delta Y is the displacement between 2 points. Let's consider the first type of the motion, which is a dropped object, or an object that is released from a certain height, which is above the ground. It is recommended that you take downwards as positive. So it depends, other educators, they prefer that you take down as positive for calculations and take down as negative for graphs. So for a dropped object, I recommend that we take it downwards as positive, because the only motion that is involved in this type of motion is downwards motion. The initial velocity of an object is 0, simply because the object is released. The velocity of an object is maximum when the object hits the ground. It has downward displacement that is equal to height of the point it falls from, which is the height of the starting point. As the object falls from 0 initial velocity, its velocity increases until it hits the ground. So we assume here that there is no air resistance or air friction. So which means the only force that is acting is gravity. So let's consider the graphs for the motion of an object that is dropped. So you can see the first one here is a position time graph. So the object is dropped. So initially the displacement is 0. So we take it down as positive. So the displacement is a curve. Why is it a curve? Okay, let's consider here the third equation. You can see that the displacement is directly proportional to t squared, with g being constant. Okay, let's consider now the velocity time graph. So along x-axis we have t, along y-axis we have the velocity meters per second. So this one is a straight line. So the object is dropped, which means the initial velocity is 0. So the velocity increases along the positive direction, which is downwards. Why is this graph a straight line? Okay, if we consider the first equation, you can see that v is directly proportional to t. So which means the graph is a straight line. So the last graph is acceleration time graph. So we have t along x-axis and g, or a along y-axis. So the graph is a straight line here. Because acceleration is constant, it remains the same, which means the graph will be horizontal. And the magnitude here is 9,8. Okay, graphs of motions. Let's check position time graph. So the gradient of the curve represents the velocity of an object. Number 2, velocity time graph. The area under the graph represents the displacement of the object. So let's check in this graph, of course, under this graph we have a triangle. So the area of a triangle is half base times height. So it will give us, for example, the height of the starting point. And the gradient of the graph represents the gravitational acceleration. So let's consider again this graph of velocity time graph. To measure here the gradient, of course, we're going to have y2 minus y1, which is v final minus v initial over delta t. And that gradient gives us acceleration. Let's consider now acceleration time graph. The area under the graph represents the velocity of the object. Let's consider this graph again. You can see the area of this graph. How do we measure this area? This, of course, is a rectangle. So the area of a rectangle is the base times the height. So to calculate the velocity, of course, it depends on the time taken. Then you can be able to get the velocity of the object. Okay, let's take the first example here. Example number 1. A stone is dropped from a bridge that is 10 meters above water level. The first question is to calculate the velocity when the stone strikes the water. Okay, let's do it together. Okay, example number 1. The height displacement is 10 meters, which is acting downwards. We also have gravitational acceleration 9,8 meters per second. It is downwards. The object is dropped, which means the initial velocity is 0. Okay, what are we looking for? We're looking for the first question, 1.1 is to calculate the velocity when the stone strikes the water. So let's check which formula to use. The quantity that is not given here is time. So let's avoid the formula with time. Let's use this one, V final equal to V initial squared plus 2G delta Y. Let's substitute. So the final velocity is what you're looking for. The initial velocity is 0. So for the equations of motions, no need to substitute the units. So G is 9,8. Delta Y is 10. So we take downwards as positive because the only direction that is involved here is downwards. So we have V final, but we're looking for V final. So we can apply the square root both sides to calculate V final and eliminate V final squared. Okay, what is the square root here? The square root is 4 meters per second, downwards. Okay, let's check the second question. The second question is to calculate the time taken by the stone to hit the water. So we can use the first equation, which is V final equal to V initial plus G delta T. Let's substitute. V final is 14, V initial is 0, G is 9,8. We take downwards as positive, then delta T. So we have 9,8 delta T equal to 14. Then we can divide both sides by 9,8 to make T the subject of the formula. So what is the answer? 14 divided by 9,8 is 1,43 seconds. Okay. 1.3, we need to sketch. Need to make a sketch. Then 1.3.1, we sketch the position time graph. Position time graph. We take downwards as positive. So along x-axis we have the time, of which you can just write it as t. Then we have 0 here. Along y-axis we have displacement measured in meters. Okay, let's check. The height is 10 meters. So the y-axis, we need to use a scale here. So we can use a scale of 2. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So of course we are controlled by the values of the position that we have. The biggest in this case is 10 meters. Okay, so if we take the starting point as the point of reference, which means the displacement at the starting point is 0. So this, of course, is the curve. This is how it looks like. So initially the displacement is 0 and the time is 0. So until, okay, the final is 10. So at the beginning, the object has a small velocity, so which means the steepness here of the graph is less initial. As time goes on, the steepness increases as the velocity of the object here increases. Okay, let's write the value of time here, which corresponds with 10. It is 1. We've calculated it in question 1.2. Is 1,43 seconds. Okay, that is the displacement time graph or the position time graph. The second question now is to sketch the velocity time graph. Let's sketch it quicker. (1.3.2). This is the velocity time graph. So we name the axis with t along x-axis, measured in seconds. Along y-axis with velocity, which is measured in meters per second. Okay, what is the biggest velocity? Of course, it is 14 that we calculated in 1.1. So we can also take a scale of 2, 4, 6, 8, 10, 12, 14, 16. It's always good to use a graph paper. So we have 2, 4, 6, 8, 10, 12, 14. So initially, velocity is 0. Initially, we have 0 velocity. When the object hits the ground, the velocity is 14. Then we can sketch a straight line. We take downwards as positive. So the time that is corresponding with 14 is the time that we calculated when the object hits the ground, which is 1,43 seconds. That is the velocity time graph. So it is positive because we choose downwards as positive. Okay, the last question is to sketch the acceleration time graph. Okay, this is 1.33. So we're sketching the acceleration time graph. So along the x-axis, we have time in seconds. Along the y-axis, we have g or a in meters per second squared. So we know that acceleration is constant and it is 9,8. So this one we don't need to use a scale because it is constant. Then we can sketch our graph, which is horizontal. Okay, we can even show that when the object hits the ground, the time is 1,43. Okay, that is the acceleration time graph. Okay, let's go back to our notes. Okay, so we're done with example number 1. Okay, we have one question, number 1.4. Without using the equations of motions, they say use the graph in question 1.32 to show that the height of the bridge is 10 meters. Okay, so 1.4. We need to show that the height is 10 meters without using the equations of motions. Remember where the sketch, which was like this, here is v, here is time. So for 1.4.1, we can use the area. So area is equal to displacement, and the area of this graph here is a triangle, which is the same as half times base times height. Okay, let's make substitution. The base here, of course, is the same as the time, which is 1.43, which is this from 0 up to 1.43. So the height, of course, is velocity from here, from 0 up to there, which is 14. Okay. Let's substitute, let's make calculations. Half times 1.43 times 14. What is the answer? It is 10.01, which is the same as 10 meters. Okay, sometimes it's not exactly accurate as 10, or it's not exactly the amount of the height, but it's always almost the same. 1.4.2. Use the graph in question 1.3.2 to show that the acceleration of the stone is 9.8. Okay, so now we need to say the gradient is the same as A, which is the same as G. What is the gradient here is y2 minus y1 over x2 minus x1. Okay, so what is y2? Of course, is v final, and y1 is v initial. So here we have delta t, or we have t2 minus t1. Let's substitute. V final is 14, v initial is 0, delta t is 1.43, or 1.43 minus 0. Okay, what is 14 divided by 1.43? We get 9.8 meters per second squared. So we've calculated, or we have proven that the acceleration is 9.8 without using the equations of motions. Okay, question 1.5. Use the graph in question 1.33 to show that the velocity of the stone when it hits the ground is the same as the value calculated in question 1.1. Okay, let's check. What did you calculate in question 1.1? Okay, it is the same as the velocity. So this is acceleration. We have t, we have g, and the value is 9.8. Okay, so the velocity here is the same as what is the area under this graph. The area under this graph is a rectangle. It is the base times height, or base times length. The base is time, which is 1.43. And the height, of course, is 9.8. Okay, let's calculate 1.43 plus 1.43 times 9.8. How much is it? It is 14. So 14 meters per second. So we've proven that using the acceleration time graph, we can get the final velocity, which is 14 meters per second. Let's go back to our notes. Okay. Yeah, so we're done with question number 1. Learners' activities that you need to do by yourself at home. The first activity, A man standing at the top of a building drops a ball over the edge of the building. The ball strikes the ground with a velocity of 30 meters per second downwards. First question, you need to calculate the height from where the ball was dropped. Second question, you need to calculate the time taken for the ball to hit the ground. Third question, you need to calculate the height of the ball when it reaches a speed of 10 meters per second. Calculate the time taken by the ball to reach a speed of 20 meters per second. Draw the position versus time graph, draw the velocity time graph, and the last question you need to draw the acceleration time graph. Okay, let's now consider an object projected downwards, which means the object is at a certain height above the ground and it is projected downwards. We take down again as positive, which means G will be positive 9.8 meters per second. Since the object is projected by launching, throwing, or shooting it down, so the initial velocity, of course, is non-zero. And if downwards is taken as positive, so which means the initial velocity will be greater than zero. If downwards is taken as negative, then the initial velocity will be negative. Since the only motion involved is downwards, then it is recommended that we take down as positive. The velocity of the object is maximum when the object hits the ground. As downward displacement that is equal to the height of the point it is projected from. As the object falls from an initial velocity, 0, its velocity increases until it hits the ground because the object is moving in the direction of gravity, which means it's going to speed up. Let's consider the graphs of motion. So this is how the position time graph looks like. Downwards is taken as positive, so which means we're going to have a curve here. Velocity time graph. Now the initial velocity is greater than 0, or it is different from 0. That is the initial, which is the velocity at which the object is projected. Then the acceleration time graph. A or G is constant, which is 9.8. So we take down as positive, so which means this is positive, 9.8 meters per second squared. Let's consider now the second example. Example number 2. The statement reads as follows. A hot air balloon moves vertically downwards at a constant velocity of 2 meters per second. When it reaches a height of 23.6 meters from the ground, a ball is dropped from the balloon. 2.1. Explain the term projectile motion. 2.2 is the hot air balloon in free fall. Give a reason for your answer. 2.3. Calculate the time taken by the ball to hit the ground after it is dropped. 2.3.2. The speed. Calculate the speed of the ball when it hits the ground. 2.3.3. Calculate the distance between the ball and the hot air balloon when the ball hits the ground. Okay, remember, the hot air balloon now is moving downwards. Okay, let's write the solutions together. This is example number 2. Point 1. Explain the term projectile motion. Projectile motion is a motion of an object in which the only force acting is gravity. That is the projectile motion. 2.2. Is the hot air balloon in free fall? Yes or no? Of course not. What is the reason? The balloon, of course, is not accelerating. It is moving at 2 meters per second. The balloon is not accelerating at gravitational acceleration, which is 9.8 meters per second. Or you can say the net force acting on the balloon is 0. Or there is a force that balances gravity. So, which means the balloon is not moving under free fall. 2.3. Calculate the time taken by the ball to hit the ground. Okay, the object is dropped, but even though the object is dropped, the balloon is moving downwards at 2 meters per second. So the ball is inside the balloon. So which means it takes the same speed or the same initial speed of the balloon, which is 2 meters per second, and it is downwards. So the object is moving under free fall. So we have G, which is 9.8 meters per second squared. It is also downwards. So what else do we have? We also have a displacement. We have a displacement of how much? 23.6 meters is the displacement. It is also downwards. Okay, so we need to calculate the time taken. We take down as positive because everything is acting downwards. Which formula to use? You can use delta y equal to the initial delta t plus half g delta t. Okay, let's substitute everything that we know. It's 23.6 positive equal to the initial is 2 positive 2. Delta t is unknown plus half g is positive 9.8. We take down as positive delta t. Okay, so we have 23.6 equal to 2 delta t plus 4.9 delta t. Let's take everything to the right. Then we're going to have 4.9 delta t plus 2 delta t minus 23.6 equal to 0. You can see this takes a quadratic form. Then you can use quadratic formula. So we're going to have delta t equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, let's substitute the known values quickly. Delta t equal to minus b plus or minus the square root of b squared minus 4ac all over 2a, which is equal to, what is b? b is 2. b is 2. We square it minus 4 times what is a is 4.9, and what is c is negative 23.6 all over 2 times a is 4.9. So we're going to have minus 2. Let's take first the plus. So what is inside the square root is 466,56. Divide by 9,8. Or we can take negative, which is negative 2 minus the square root of 466,52 all over 9,8. Okay, let's punch the calculator quickly. How much are we getting? So negative 2 plus the square root of 466,56 all over 9,8. So we get 2, the answer is 2 here. So it's 2 seconds. On the other side, you can see the other side will, of course, be negative. So this is negative and time cannot be negative. Therefore, t is 2 seconds. So we have t. So I know that many students, they don't like using a quadratic formula. So if you don't like using quadratic formula, then what you can do, you can start by calculating a velocity. Then after getting the final velocity, now you can use v final equal to v initial plus g delta t. To calculate the final velocity, you can use v final squared equal to v initial squared plus 2g delta y. Okay, let's go now to the next question. We need to calculate the speed of the ball when it hits the ground. We need to calculate the speed when the ball hits the ground. 2.3.2. Okay, let's check what do we have. So we have initial velocity of 2 meters per second downwards. We have a height of 23,6 meters, which is also downwards. Okay, let's calculate it together. So which formula must we use? We can use V final equal to V initial plus G delta T. Let's make substitution. Initial velocity is downwards. We take down as positive. So it's 2 plus 9.8 G is downwards. We take it as positive. Time is 2, which is also downwards. Okay, let's make calculations. Quick one is 2 plus 9,8 times 2. So the answer is 21,6. So we're getting 21,6 meters per second. Okay, let's go now to the next question. It's to calculate the distance between the ball and the hot air balloon when the ball hits the ground. Okay, that is 2.3.3. Okay, let's calculate the distance of the balloon. So the balloon is moving at a constant speed. So which means we have, let's call the distance of the balloon x. So we have x, which is vt. The speed of the balloon is constant, which is 2. So the time taken by the object to hit the ground, okay, we've calculated it. In the first question, we got 2. So we substitute 2. 2 times 2 is 4 seconds. Okay, so now we can say the distance will be equal to, of course, the height, which is 23,6 meters minus this 4 meters. minus 4 meters, which is the distance traveled by the balloon downwards. Okay, let's get the answer. So we have 23,6 minus 4. The answer is 19,6. 19,6 meters. Okay, let's go back to our notes. So do you have any question? Okay, that's all. So we're done with example number 2. Let's now go to learner's activity number 2. Okay, a man is on the top of 20-meter high building. The man throws a brick vertical down with a velocity of 2 meters per second. Ignore the effect of air resistance. The first question is to calculate the time it takes to reach the ground. The second question is to calculate the velocity of the brick when it reaches the ground. 2.3, calculate the height of the brick when it reaches a speed of 4 meters per second. 2.4, you need to draw the position versus time graph. 2.5, draw the velocity time graph. 2.6, draw the acceleration time graph. Please do this by yourself at home. Let's now consider an object that is projected vertically up and falls back to the starting point. Okay, if it is the case, we take up as positive, which means G now will be negative 9,8 meters per second squared because G is acting downwards. The object has a non-zero initial velocity, which means the initial velocity is greater than 0 since we took up as positive. The displacement of the entire motion is 0 because the object falls back to the starting point. The object slows down as it goes up simply because it is moving against gravity. Then it reaches the maximum height. It stops at the maximum height, it turns around, then it starts falling. At the maximum height, the object's velocity is 0. As the object falls, its velocity increases until it hits the ground. It increases simply because the object is moving now in the direction of gravity, which means it's going to accelerate. The time taken to reach the maximum height is the same as the time taken to reach the ground from the maximum height, which means T up is equal to T down. So this is the motion or the trajectory of an object. So the object is projected from the starting point, which is A. As it goes up, its velocity of course decreases until it reaches the maximum height at point B. Then at point B, it turns around, then it starts falling. As it falls, of course, its velocity increases until it hits the ground at point C. So now we say the time taken to reach B from A is the same as the time taken from B to C. So which means TAB is equal to TBC. Another thing that is important is the initial velocity at A is the same as the final velocity at C, but in the opposite direction. For example, if the velocity here is 6 or is 5, for example, the object is projected at 5, we're going to have initial velocity which is 5 meters per second upwards. Then at C, we're going to have a final velocity which is also 5 meters per second, but it will be downward. So for motion AB, of course, the initial velocity is the velocity in which the object is projected, but the final velocity is 0. For motion BC, the initial velocity will be 0, and the final velocity will be the velocity when the object hits the ground. Okay, let's consider now motion AB. The object is projected up, down is taken as negative. So which means for motion AB, G is negative 9,8 meters per second squared. Then the initial velocity is greater than 0. The velocity decreases as the object rises. At maximum height, the velocity is 0. So V final is 0. Delta Y, of course, is the same as the height AB. Then the time taken to reach B is the same as T up, which is also the same as T down, which is TAB. This is how the graphs looks like. Up is taken as positive. This is the graphs for motion AB. Motion AC now, which is the entire motion. Motion AC is the motion from A to C, the entire motion. Up is taken as positive, which means G is negative 9.8 meters per second squared. V initial is 0. The displacement is 0. V final is the same as V initial, but in the opposite direction, which means it is negative. T is the same as the time taken for motion AB, which is T up, or T is the same as T up plus T down, which is the same as TAB plus TBC, or it is the same as TAB times 2. This is how the graphs looks like, position time graph. So it looks like this. Velocity time graph looks like that. Then the acceleration time graph. Let's consider now the third example. A soccer player kicks a ball straight up into the air at 6 meters per second. Ignore air friction. 3.1, we need to calculate the maximum height the ball reaches. Okay, let's do that together quickly. Okay, let's do that quickly together. Example 3. The first question is to calculate the maximum height the ball reaches. Okay, let's check what do we have. Example number 3. Let's check the initial. Okay, we have the initial velocity, which is 6 meters per second up. Okay, let's do it together. So we have the initial velocity, which is 6 meters per second, which is upwards. So what else do we have? We have G, which is 9.8 meters per second squared, which is downwards. We're looking for the maximum. So at maximum height, V final is 0. Okay, so we have initial velocity, which is 6 meters per second, it is upwards. So we also have G, which is 9.8 meters per second squared. So 3.1.1, we're looking for the maximum height. So we can use this formula, V final squared equal to V initial squared plus 2 G delta Y. Let's substitute. V final is 0, V initial is 6, the square. We take up as positive, then down is negative. times delta y. Okay, so we have 0, 6 squared is 36, 2 times negative 9,8 is negative 19,6 delta y. We take the negative 10 to the left, it becomes positive. Then we can make delta y the subject of the formula. We divide both sides by 19,6. Okay, what is delta y? We divide 36 by 19,6. What is the answer? The answer is 1,84 meters. Okay, the next question is to calculate the time taken by the ball to reach the maximum height. Okay, let's do it here. So this is 3.1.2. We're looking for t. Now we can use this formula v final equal to v initial plus g delta t. Let's substitute the known values. The final velocity is 0 at maximum height. The initial velocity is 6, we take up as positive. G is 9,8 delta t. We take the negative 10 to the left, it becomes positive. Then let's divide both sides by 9,8. Then what is t? Delta t is 0,61 seconds. Okay, let's go now to 3.2. 3.2, we need to draw the position time graph. Okay, let's draw the position time graph. Position time graph. So along the x-axis we have time in seconds, and along y-axis we have delta y in meters. Okay, so we can use a scale of 1, 2, 3. So the maximum height, of course, is 1,84 that we have calculated. We can estimate it somewhere here and write it. This is 1,84. Okay, then let's sketch our graph. Goes up, it reaches the maximum height, then it falls. Okay, let's indicate the time taken to reach the maximum height is 0,61. Of course, the time taken to get back to the starting point is 1,22, which is the double of 0,61. Okay, this is how the sketch looks like. Let's now sketch the velocity time graph. So 3.2.2 is the velocity time graph. Okay, velocity time graph. So along the x-axis we have t in seconds, origin is 0. Then along y-axis we have velocity in meters per second. Okay, let's see, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is 6 is the starting point. So the journey is going to end somewhere here at -6. Let's sketch the straight line. This is how it looks like. So at maximum height, V is 0, and the time there is 0.61. The object hits the ground at time 1.22. That is the velocity time graph. Let's now sketch the acceleration time graph, which is the last one. So this is 3.2.3. This is acceleration time graph. Okay, let's sketch it. So here we have t in seconds along x-axis, 0, then along y-axis we have g in meters per second squared. So we took down as negative. So this is 9.8. This is how the graph looks like. It is 9.8 up until the time of 1.22 seconds. Okay, that is the acceleration time graph. Okay, let's go back to our notes. Okay, learner's activity number 3. The graph below shows the motion of brick that is thrown vertically upwards from the ground. It takes 1.4 seconds to reach its maximum height, after which it falls downwards and is caught by a person on a scaffold building a wall for a house. Ignore friction. Okay, you can see we have a sketch there, which represent the motion of the brick. 3.1. What does position Y represent on the graph? You see Y there? 3.2. Write the value of the time t without performing any calculations. 3.3. At what time will the velocity of the brick be 0? 3.4. What is the acceleration of the brick at position 9.6 meters? 3.5. What is the direction of the acceleration after the following time intervals? 3.5.1. 0.6 seconds interval. 3.5.2, 1.4 seconds interval. 3.5.3, 2 seconds interval. 3.6. Calculate the initial velocity of the brick. Calculate the magnitude of position Y. Calculate the velocity when the brick is cast. That is 3.6.3. Which means you need to calculate the velocity when the brick is caught. Then sketch the velocity versus time graph. Clearly show the following on your graph: the initial velocity and the corresponding time, the velocity at the maximum height and the corresponding time, the velocity when the brick is caught and the corresponding time. 3.7.2. Sketch an acceleration versus time graph for the motion of the brick. Clearly show the gravitational acceleration. Learners activity number 4. A group of grade 12 learners developed an experiment to investigate the change in position over time of an object dropped from a certain height. They used a small sphere, 1 meter ruler, and a camera that takes photos every 0.1 seconds. The table below shows the results obtained during the investigation. We have t in seconds and also y for displacement in meters. 4.1. Describe the method used to perform the investigation. 4.2. What is 4.2.1 the dependent variable? 4.22 the independent variable. 4.3. Draw a graph of position versus time and the graph of position versus square time or time squared. 4.4. What conclusion did learners make from the shape of the graphs? 4.5. And add a third row to the table for the velocity of the sphere at the end of each time interval. So which means you need here to put the third, row with a v in meters per second. Draw a velocity versus time graph. What is the conclusion from this graph? 4.8. What quantity does the slope of the graph represent? Then 4.9. Draw the acceleration versus time graph. That is the last question. Okay, ladies and gentlemen, this is the end of the lesson. Thanks for taking part of the lesson. Learn, grow, and succeed. Thank you.